What specific problem does the Agent Workflow Memory (AWM) method address in current language model-based agents? Please elaborate on the motivation behind proposing this method.
The Agent Workflow Memory (AWM) method addresses the problem of current language model-based agents' lack of robustness and adaptability when faced with changes in task contexts or environments. These agents typically rely on a fixed set of examples, which limits their ability to learn from past experiences and adapt over time. The motivation behind proposing AWM stems from the observation that humans abstract common task routines from their experiences and apply this knowledge to guide future activities. AWM aims to replicate this human-like learning by inducing reusable workflows from agent trajectories, allowing agents to capture essential skills needed for increasingly complex tasks. By integrating these workflows into agent memory, AWM enables agents to continuously learn and improve their performance across various tasks and environments, significantly enhancing their adaptability and success rates.
How does the proposed AWM method work? Please illustrate the step-by-step process, including the key components and the interactions between them.
The proposed Agent Workflow Memory (AWM) method operates through a systematic process of inducing, integrating, and utilizing workflows to enhance agent performance in web navigation tasks. First, AWM begins with a set of past experiences, each comprising a natural language task instruction and a corresponding action trajectory. An induction module, denoted as I, processes these experiences to extract reusable workflows, which consist of a high-level task description and a series of actionable steps. These induced workflows are then integrated into the agent's memory, augmenting its existing knowledge base. When the agent receives a new task instruction, it utilizes this enriched memory to generate actions, effectively leveraging the workflows to improve task-solving efficiency and success rates. This iterative process allows AWM to adapt and build increasingly complex workflows over time, enhancing its ability to generalize across different tasks and domains.
Can you provide a specific example demonstrating how AWM induces workflows from agent trajectories? Walk through the example and explain each main step in detail.
An example of how AWM induces workflows from agent trajectories can be illustrated through the task of finding a place by its name. Initially, AWM starts with a basic set of built-in actions and processes a few examples related to this task. As the agent navigates the environment, it generates an action trajectory, which consists of observations and actions taken to solve the task. For instance, the agent might observe the state of the environment, recognize the name of a place, and then execute actions like click or type to search for that place. Once the agent successfully completes the task, this experience is recorded as an experience, E, which includes the natural language instruction and the sequence of steps taken. The induction module, I, then analyzes this experience to extract a reusable workflow, which is represented as a high-level goal description and a series of steps that encapsulate the essential actions needed to achieve the task. For example, the induced workflow might summarize the process as find a place by its name and detail the steps involved, such as search for the place and confirm the location. This workflow is then integrated into the agent's memory, allowing it to leverage this knowledge for future tasks, thereby enhancing its efficiency and adaptability in similar contexts.
What are the primary benefits of using AWM in comparison to traditional methods? Highlight improvements in areas such as performance metrics, efficiency, and adaptability.
The primary benefits of using Agent Workflow Memory, AWM, compared to traditional methods include significant improvements in performance metrics, efficiency, and adaptability. AWM achieves a 51% relative increase in overall success rate on the WebArena benchmark, outperforming the top published autonomous method and even surpassing human expert augmented methods by 7.9%. In terms of efficiency, AWM reduces the average number of steps taken to solve tasks, completing tasks with about 2.0 fewer steps than the BrowserGym baseline and 48 fewer steps compared to the AutoEval method. AWM's adaptability is evident as it continuously induces and integrates workflows from both past experiences and real-time interactions, allowing it to generalize effectively across different tasks, websites, and domains, as demonstrated by its superior performance in cross-template and cross-domain scenarios. Overall, AWM's ability to learn and apply reusable workflows enhances its robustness and performance in dynamic environments.
How was AWM validated in the experiments, and what specific metrics or benchmarks were used to gauge its effectiveness?
AWM was validated through experiments on two major web navigation benchmarks, WebArena and Mind2Web. In WebArena, AWM was evaluated based on its overall success rate, where it achieved a 51% relative increase compared to the baseline BrowserGym and outperformed human expert augmented methods by 7.6%. The evaluation metrics included the average number of steps taken to complete tasks, with AWM demonstrating about 2.0 fewer steps per example than BrowserGym. In Mind2Web, AWM's effectiveness was gauged using stepwise success rates, where it achieved a 24.6% relative improvement over baseline methods. The experiments also included cross-task, cross-website, and cross-domain evaluations to assess AWM's generalization capabilities, with significant absolute point improvements reported across these scenarios.
What limitations or challenges were observed with AWM during the experiments or its implementation? How could these issues potentially impact its applicability in real-world tasks?
During the experiments, one limitation observed with AWM was that it sometimes led to lower action F_1 scores compared to the MindAct baseline. This was attributed to the augmented workflows, potentially guiding the agent to take actions that were not always relevant to the specific environment state, indicating a challenge in discerning when to diverge from workflow guidelines. Additionally, while AWM improved element selection accuracy, it could lead to incorrect workflows if the model predicted trajectories that were not accurate, which could degrade overall performance. These issues could impact AWM's applicability in real-world tasks by causing agents to follow suboptimal action paths or make incorrect decisions based on flawed workflows, ultimately affecting their effectiveness in dynamic environments. Furthermore, the reliance on induced workflows may limit adaptability in scenarios where task contexts vary significantly from those encountered during training.